welcome back to your favorite intermediate algebra course. It's good to see you guys. We're going to take a look today at function operations, okay? Our objectives here are just to perform some operations with functions. And then we're also going to look at, so your typical addition, subtraction, multiplication, division operations, as well as compositions, okay? So if you're looking at this screen here in green, I wrote down a bunch of operations. The first one there being if you're creating a new h of x function, okay, and it's defined by f of x plus g of x right there. Well, you take your f of x and then you add in your g of x. You notice up above there I've defined f of x and g of x there, okay? So you end up with 3x plus 1. Now if you're subtracting them, be careful because that x plus 1 is a binomial, so you have to end up distributing that subtract, and then you combine your like terms. So h of x ends up being x minus 1. Okay, h of x is x minus 1. So that's if you're finding the difference of two functions. Okay, and multiplication, f of x times g of x, and you see it there, 2x times x plus 1, and you end up with your solution there. And finally, f of x over g of x, your division operation, okay, 2x over x plus 1. Now, when you're doing these things, you want to consider the domains as well, okay? So the domain of this new h is all x values that are in the domain of both f and g. So like for the first one, h of x equals 3x plus 1. And you say, well, I got no restrictions there on either 2x or x plus 1. So I'm going to have no restrictions on h of x. It's all real numbers, okay? And then h of x is f of x minus g of x. Again, no restrictions on f or g. So both the difference operation and the multiplication operation there are going to be all real numbers. But notice on the last one there, h of x equals f of x divided by g of x. You see that? 2x over x plus 1, and you're thinking to yourself, well, what makes that x plus 1 undefined? Well, that x plus 1, that denominator there cannot be 0, right? We're undefined. So we cannot have an x value of negative 1. So the domain for this one is all real numbers except for negative 1. Okay? So all real numbers except for negative 1. Or if you want to put it in interval notation, you can do that. You're anything up to negative 1, you put a parenthesis because I do not include negative 1 union, and then we take off from negative 1 to positive infinity. Okay, so just think to yourself, hey, I cannot have negative 1 on that one there. Okay, all right, let's do some more examples here. So let's say let's let f of x be 3x to the 1 half, g of x be 2x to the 1 half. Okay, so what would f plus g look like, and what's the domain on that? So you say, well, f is 3x to the 1 half, g is 2x to the 1 half, or if you want to think about that, 3 root x plus 2 root x. So I got 5 root x, right? Those are like terms. Okay, and then your domain on that one, both f and g have the same domain. You know, x cannot be any negative number, right? Isn't the square root of x, doesn't the square root of x look like that, right? In other words, that's my domain on that. Well, same thing for f and g, they have the same domain, and h, 5 root x, is going to have that same domain when we add those two, okay? Let's do b now. Let's do the difference. So f minus g, so 3 root x minus 2 root x. 3 minus 2, 1 root x, which would just say root x. So again, the domain on that one, x such that x is anything greater than or equal to 0. Okay? The domain, we're only staying in the real numbers here, right? So x being anything greater than or equal to 0. Like we can't have the square root of negative 1, right? We're going to be working with imaginary numbers if we do that, so we're going to stick to real numbers here. Okay? All right, let's do another one. How about Okay, let's find their product first of all. So we have this 2x times x to the 1/2, or another way to think about that is 2x times the square root of x, right? Now you notice g has a restriction, right? It's not just all real numbers. What's your domain on that one? Well, we know it's got to be greater than or equal to 0, right? Again, we can't have like the square root of a negative number, like square root of -3, can't do that in the real numbers. Okay, so this domain, okay, both f and g have to be you have to consider f and g, and so since you have in g non-negative real numbers, what happens when you take the product here is you're going to end up with, now consider it when you're simplifying this, 1 plus the 1/2, so 3 halves, all right? 2x to the 3 halves. Now here's h of x, okay? And think about that, by definition from last section, or maybe it was the section before, we had 3 halves is x to the 1/2 to the third, right? So power of a power there. Okay, so you think about, well, that is that, right? So you have that restriction on this domain before you take the third power on that. Okay, so the domain of this thing, the domain here, x greater than or equal to 0. Okay? Let's do the quotient. So, alright, so here we got f of x, 2x, over the square root of x. Okay? Now think about this before I simplify this. Okay, 2x on the top, I got no problems. X can be anything, right? But that square root of x on the bottom, now we're saying I can have non-negative real numbers. So initially we're thinking x greater than or equal to 0. But if I think about that further, can I have a 0 underneath that square root of x? I cannot have 0 there because I'll have the square root of 0 right here, which would be 0, which gives me 0 in my denominator, which means it's undefined. So it's not greater than or equal to. I have to say simply greater than 0. That's going to be my domain on this thing before I even simplify it. Okay, so I'm greater than 0, so all positive real numbers. Now let's go ahead and simplify this. So this is 2x over x to the 1/2. So 2x, remember this is x to the 1, right? So 1 minus 1/2. So 2x to the 1/2 or 2 root x. Okay, that is the simplified form there. Okay, so that's adding, subtracting, multiplying, dividing. Those are your 4 operations with 2 functions. Okay, now let's get to composition of 2 functions. All right, so here's your definition. The composition of 2 functions. The composition of the function f with the function g is f of g of x. Okay, so they write this a few different ways. So f of g of x, this is the same thing as f of g of x. Okay, and then we'll talk about the domain here in just a second. But if you notice this mapping, it's showing you the mapping. So what you're doing is you're taking an x value. Okay, you take this, do it in blue here. You take this x value. Okay, so here's your x value. Okay, and you're running g on that. Okay, so we're running it into g. Okay, and it spits out g of x, right? It spits out like a y value. So that's my output. So I get g of x. And now g of x becomes, this g of x is now my input for f. Okay, so I run f on g of x. Okay, and this is called f of g of x. So another mapping you might see in textbooks is they say, well, let's take this x, run g on it, and it spits out g of x, right? And now I'm going to take this g of x, and I'm just going to run f on it. And so I end up with f of g of x. That's my output. Okay? And now the mapping, I do like this mapping that I have here on this slide because it does show you the domain as well. Okay? So the domain on this thing sorry, let me rewrite that. Was bugging me with the blue on there. The domain on this thing is you have to, the domain of H, so the final domain of f of g of x is a set of all x values such that x is the domain of G, so you have the restriction. You have to think about what's my domain of G, and then G has to fit into the domain of F. Okay, so that can get a little tricky at times, but let's talk about running this composition first of all. So let's say we have, for example, let's say we have f of x equals 2x to the negative 1, or in other words, 2 over x to the 1, right? And then let's say g of x is x minus 1. Okay? What would you say if we just asked you to find this first of all, f of g of 3? Okay, what would you do to find f of g of 3? And I say, well, I can do g of 3 first of all, right? So let me go to the side and let me say, okay, here's my g of x. What would g of 3 be? So I'm plugging in 3 for x, and I get 3 minus 1 is 2, right? G of 3 is 2. In other words, when I plugged in 3 for x, my output was 2. My y value was 2, right? So I say, what was g of 3 equal to? 2. Now, I just got to find f of 2, okay? So now we just say, well, what was f of x? F of x was 2 over x, right? So let me go over here. F of x is 2x to the negative 1, so 2 over x, right? So what is f of 2? 2 over 2. F of 2 is 1. So let's go back to the original problem. So it said, what was f of g of 3? That's equal to 1. Gave me a final answer of 1, right? Because remember, f of 2 was 2 over x. 2 over 2, which is 1. Okay? So you run the g, you run this interior one first. It's kind of like two problems in one. You find g of 3, and you plug that answer into f, don't you? Okay, you plug that answer into f. Let's do, let's try a different one. Let me go the other way around. Let's try, how about g of f of 1? G of f of 1. So I said, well, first of all, I got to figure out f of 1. So let me go to the side and let me write f of x. F of x is 2 over x, right? I got to find f of 1, 2 over 1, which is 2. F of 1 ends up being 2. So now I got to find g of 2, right? G of 2. So what is g of x? X minus 1. So what would g of 2 be? 2 minus 1. So g of 2 ends up being 1. So in other words, g of f of 1 is 1. G of f of 1 ends up being 1. Okay, so you take it little by little as you do that. You know, I'm really enjoying this problem. I better do another one. This is great. How about g of g of 7? That's a good one. G of g of 7. All right, I got to find g of 7, right? So I go to the side and I say, what's g of x? X minus 1. What's g of 7? 7 minus 1. 6. G of 7 ends up being 6, so I replace g of 7 with 6. And now I say, okay, I'm running g of 6 now. What's g of x? G of x, x minus 1. I'm plugging in 6 now. Aha, g of 6 is 5. In other words, g of 7 is the whole problem that we did from the beginning, right? Ends up being 5. Hey, how cool is that? Let's do some more now. Let's keep it a little more abstract.